All right, so today we're going to talk about data structures, the struct keyword. We're going to talk about linked lists and arrays of data structures. So just to have a place to edit things, I'm going to make a file so that I can start adding code to it later. I'm going to call it J23 for July 23, touch J23.c. And I'm going to open that up with my text editor. All right. I'm going to go ahead and include stdlive.h because I know that we need that for malloc. And since I'm doing this with Cygwin and GCC, I'm not going to add any system pauses or anything like that. So I posted a note about it, but I was reminded that strupper and str lower, string upper and string lower, are non-standard, that they're not in every version of the C libraries. So I posted the source code that you could go and Google up for a version of string upper. I'm just going to copy this from the front page and put it into my code. So strupper, parentheses, char, asterisk, str, open brace, char star s for s equals str, semicolon, star s, semicolon, and s plus plus, and then star s equals to upper, parentheses, unsigned char star s, and a return string. So this is treating strings and pointers interchangeably, right? Because a string is an array of characters, and so we declare a pointer to that array, or to a character, and we set that one's address equal to the address being passed in, which is the address of the array, and then we step through it, and as long as that character has any data, as long as it's not any null, it will iterate through them, assigning data to the address, to the dereferenced address of that, equal to the uppercase version of that character. And let's see if it works. I'm going to make a string, char name is equal to Joe, and then strupper name, and I'm going to print it out. Printf uppercase name equals %s \n end quote comma name. GCC J23.c. Return makes integer from pointer, implicit declaration of function to upper. Oh, yeah. Okay, so what does it do? It returns a pointer to a char star str upr. And I left that off my note. I apologize for that, guys. I'll fix that. Going in and adding the return type of strupper, which is char star. But if you're not going to use its return value. But anyways, we had to have that in there, or else we'll get warnings when we compile, which we don't want. Try that again. Have I not fixed it? I thought I did. Maybe I didn't save it. And we don't have to upper included yet, so include string.h to get to upper. # include string.h. Really? Did I not save it again? Oh, for Pete's sake.
Yeah, C-type.
No, it's in C-type? Okay. Okay. All right. So one last pound sign includes C-type.h. Much better. Dot slash A to run it, and the name has been uppercased to Joe. Now when you're ready to turn it lowercase, just copy the whole shebang, and everywhere rename it from str upper to str lwr, and make this 2 upper equal to 2 lower. Now, did you have to do it that way? No, not at all. You could have just run this a loop on your string, calling 2 upper or 2 lower.
Oh, so you only have to do a prototype if your function is not at the beginning?
Correct. If your functions are above where they're being invoked, the prototype's only necessary to forward declare it so it knows it. Yeah, that's right. We don't have to make prototypes for these just because we've declared them above main. Okay, if I hadn't wanted to write a function for that, I could have just done a for loop. Int I is equal to 0, for i's equal to 0, I is less than 3, I plus plus, this is sloppy programming. And then name subscript I equals 2 lower, name subscript I. It's just nice to have a function to do it, but you could do it that way anytime you wanted to. So now I'm going to print it out again and print out the lowercase version. I'm going to take out the braces to give myself a little bit more room. All right. So that's my string lower function. Looks remarkably like the string upper function. But then I just also demonstrated using a for loop to rip through it directly without using a function. So this is rather cryptic, how this function works. What it's doing is, we could do this. S is equal to str, and then we could eliminate that one. We could move that s plus plus to a line by itself. You don't have to make all these changes. And then what this really is saying is while star s is not equal to 0, or while that specific character is not equal to null, like that. That looked odd. That is a rewrite of it. I don't know if that makes it easier to understand what it was doing with its pointer manipulation. Maybe.
What is an unsigned char?
You know what? I don't know why that's there. What would happen if we remove that? Yeah, I don't see why that's necessary. So it's setting our array pointer equal to the first position in the string, and then we're going as long as we're not looking at a 0, a null. We're going to take that character, we're going to turn it to uppercase and store it back into itself, and then we're going to increase our pointer by 1 so we keep going through the string.
So it's checking by character, right?
Right. And so since JOE and then has a 0 at the end of it, it would take that J, the first character in the array is a J, and so it would take that character, turn it to upper, store it there, and then it's going to add 1 to our pointer. So now our string actually points to the second character, which is the O. And so it would copy the lowercase o, turn it uppercase, and put the uppercase o back into its position, and it adds 1 to the pointer again. So now it's pointing to the E. The E gets copied, the uppercase version of it, and put back in. And then we add 1 more to the pointer, and now it's pointing at a null character, the one that marks the end of the string.
Wait, how does that work? Because you're only changing the first one.
That's what it looks like, right? But then I increment the pointer itself.
Oh.
And so if I, yeah, this could be fun. Print f %s \n end quote comma and then our string. And I'm just going to comment this out, but what we're going to see is that it equals to the word Joe and then OE and then E and then nothing. So each time that S++ happens, it points, it kind of chops off the first character of the array. That's a bad way to put it. The correct way to put it is to say that the pointer is incremented so that the array now starts at the O, and then now it starts at the E, and then lastly it now starts at the the null, but it exits a while loop at that point. And if that bugs you to word it like that, go back to the way it was worded previously. That's how it was worded previously, in effect. Is that a little more solid? Okay. Okay, cool. All right, I'm going to undo all my changes.
You can just do it the other way, so you don't have to use the W variable. Again.
I'm sorry, pardon me?
Never mind.
I'm still going to take that unsigned char out after I'm done writing all this, or undoing everything. Okay.
What do you have an unsigned char? Like, what does that even mean?
Yeah, what's the difference between a signed and an unsigned char? Let's Google that one up. An unsigned char is a byte value. The regular char is signed, so you have 128 values. But an unsigned char versus signed chars versus unsigned chars, these are supposedly all distinct character types. If you're using them for text, just use char. If you're using the types as numbers, go ahead and use signed or unsigned. Now in our case, we're just using them for text, so we didn't need to specify whether it was a signed or unsigned.
Why would you use them as numbers?
Because it's a byte. If you feel like storing a number that's only 1 byte, and you want your byte, to be treated as a value between 0 and 255, then you could use an unsigned char.
So a char is only a byte?
Right.
But if you were to use like an int, it would be like 4 bytes?
Exactly.
Huh.
Exactly.
That's good.
Yeah, so a character is 1 byte, so if you want a specific, just a value to hold only 1 byte, then you could use unsigned char. Or you could use a signed char if you wanted values in from -127 to +127. Since we don't care about those, we just could do away with that casting entirely and be done with it, in my opinion. Okay. Whoopsie, whoopsie, whoopsie. Have I downloaded the next PowerPoint? Let's take this unsigned char out in our example as well. Alright, so this PowerPoint actually isn't very long. I did not get very far in the chapter before I started working on the linked lists. And it's actually chapter 9, not 8. Sloppy. Alright, so to define a structure, you use the struct keyword. You define the structure there, and then if you feel like defining a variable of that type, you can just put that before the semicolon. Like if I wanted to create this structure and then I wanted to create a variable of that type, I could have done the whole struct, but then before the semicolon put the word a problem there. Normally you're not going to want to do that. Normally you're going to want to wait and create your variables. And so separating them, you define your structure like that, and then you declare a variable using the struct keyword again, but then the name of the structure and then the variable. And you can put more than one variable there if you want. That's different than how you would do it in C++, where you would leave off the word struct. You would just do math, a problem. So to create a variable like that, struct math m1, or if we want to initialize all the members of it, x, y, and result, we could do struct math m2 and then fill those in. And x would then equal 1, y would equal 2, and result would equal 3. So once you create a variable of that type, you can assign its values individually, or address them individually. m3.x is equal to 1, m3.y is equal to 2, m3.result is equal to 3. And that would fill in the values in this. So the book shows a different way of using typedef in struct than what I've been showing you so far. They use typedef, and then they give the whole structure definition right there. And then lastly, they give it a typedef name. That works. Maybe it's even more common than my style. My style is to define the structure first, and then use a typedef to, well, that's wrong. It should have said typedef struct employee. Employee, capital E. Well, so this slide's completely wrong. If I'd done that correct, it would have this struct definition there, and then it would say typedef struct employee space employee with a capital E. And once you did that, you could define your employees the same way. Employee E1, comma E2.
So are structs like objects?
Exactly. They're like a Java class without members, without functions, without methods. So they're data-only classes in effect. So they are objects. Let's go ahead and define a struct of some kind. I'm going to go up here to main. Struct animal. And every animal has a name and an age in years. Now I'm going to do a typedef so that I can... Nah, I'm not going to do the typedef. Forget the typedef. Okay, so here I'm going to create an animal. So struct animal dog. Why don't we make one more member, which is going to be species. So char name, subscript 80. Char breed, subscript 80. And int age. Okay, so struct animal dog is equal to, and let's initialize those things. This is Lassie. Lassie is a collie. And Lassie is 14 years old. And we could print those members out. Printf animal name equals %s, comma, breed equals %s, comma, age equals %d, \n, end quote, comma. And then we're going to fill in, I don't know why I capitalized dog, dog dot name, comma. I'm going to put those on a separate line. My line's getting long. Dog dot breed, dog dot age. And so it printed out that the dog's name is Lassie, that it's a collie, and that the age is 14.
So what does that type def in the slides do?
The type def just makes it so that you don't have to use the word struct to make it look like C++ or Java.
Okay.
Right. So we could do type def struct animal and whatever you feel like calling it, but I'm going to call it animal with an uppercase A. Now that I've done that, I could create my animal just like this.
Just type animal. Yeah.
Right.
So why would you use a type def over just doing like a preprocessor define? What's the point?
Why would you use type def instead of a preprocessor? Debuggers and things like that don't really understand preprocessing. So when it's looking at it, you might not be able to hover your cursor over that preprocessor, hover your cursor over animal and have it know what it was, or to be able to right click on it and do, go to definition and have it go to the right place. So preprocessors are great if for stitching things together kind of, but if there's a C way of doing it, I would rather do it that way, because if you're using a sophisticated editor that is context sensitive and things like that, then the editor will know what an animal is, whereas if you merely use a preprocessor to define a macro to mean that, then it doesn't. It still works and it still compiles. It's just that the editor doesn't know what it is.
My age is not printing 14, it's printing
Oh, I wonder if mine is.
gibberish.
Did you put %d?
Yep.
Okay, somehow magically mine worked. Let me come look at yours.
Do int I equals dog, oh, let's use another variable we used I later on, x equals dog dot age. So int x equals dog dot age. Age, oh, sorry.
Oh.
AGE, yeah. And then semicolon, and then print that out. Just print out x. Print out. %d, yeah. Let's see. Oh. See what you're missing there? Breed equals S. Yep, yep. So it's actually, you only had two placeholders, and name was going into that one and breed was going into that one.
Okay.
Yep.
That's weird. normally wouldn't it, if you only have two, you know, like if you put 3 there and you only give 2 arguments, it would give you an error. But if you only put like 2 and then you give it 3, it won't give you an error.
Right, right. Yeah. If you give too many arguments here, the compiler doesn't consider that an error. It just fills in and ignores the rest of them. And when I say the compiler, that's not the right term because the compiler doesn't care how many. But right, it doesn't automatically generate an error if we have too few. If we have too few placeholders to meet the number of arguments. Oh, and I left it going the whole time. Oh well. Hope everybody sitting at home enjoyed that little pause in the show. Okay, so you can write functions that will accept structures. Let's do that. Let's write something called print animal, or just print A. And so it's going to take a struct animal an, short for animal. And it's just going to do the same thing as this printf statement did, so I'm just going to copy that. Copy that printf, paste it, and replace the word dog with an.
I'm confused.
And now I'm going to print it out. So I'm going to call print A, and I'm going to pass that dog into it.
How can you put struct animal an as your argument to the function? How does that work?
Same way you were defining the animal. Just like if we had int x and we wanted to pass something in, as a function.
No, but I mean, like, wouldn't you just put struct an? Like, why is it animal?
It has to know what structure it is.
Oh, so it can't just take any random structure?
Well, the variable name can be anything you want, but whatever comes here has to be the name of a structure that you've created.
Okay. So it can only, when you write your function, it can only take a structure that already exists.
Exactly, right. This part is the type declarator, and this is the variable name, and it has to be a type that you've already created. One of our types is struct animal. It'd look a little bit clearer if I used my type def instead and called it animal like that. All right, let's see if it worked. It should print out Lassie twice now because I'm calling our function, invoking our function. Well, I'm just going to comment that one out, I guess. Okay, and it did print out the animal's name and breed and etc. Now that's passing by copy, passing by value. The entire structure is being copied in. You might want to pass a structure in as a pointer. Why? Because passing a single 8-byte pointer could be a lot less expensive. This is it's a small structure, but it's 160 plus an int is another 4. It's 164 bytes long to pass this around like this. But if we define it as a pointer, we are only passing 8 bytes in rather than 164. So void print AP, animal by pointer. Struct animal star PAN, pointer to animal. And again, we can just copy that line, but we have to make more changes than just changing the AN to PAN. We have to make one more change to it. It needs to be PAN, and then instead of dot, we need to use dash greater than. And you Java users who are used to seeing the dot, you're not used to seeing this. This is a C-specific thing. Why don't you see it in Java? Because Java doesn't have pointers, so you never need to dereference them or access them in this way. So I'm going to print the animal by its pointer this time. How do I get the address of that variable?
And
Yep, so I'm going to use ampersand dog. Okay, and so those functions displayed equivalent output. So just remember that if you're going to access something, access a member of a structure of an object from its pointer, you use that. But of course there's the alternate way of using a star, right? Which would look like this. Star PAN dot name, star PAN dot breed, and star PAN dot age. Those are the exact same thing, it's just the syntax is different. What this says is resolve that pointer, dereference it, turn it into the data that you're trying to access, and then get a hold of the name, the breed, and the age members. Or what do you know? See, the syntax starts to look a little ugly. You'd probably just as soon use those. Yeah.
so, let's say you ran the first one. Let's say like I wrote a program and it had like a button where it would keep running the first function. Would every time I run it, it would just take up more memory?
It's not that it would take up more memory, because when the function returns, then the memory that was required to pass that in is gone, but it just takes more time.
Okay.
Because
So
it's
it
caught.
cause like a memory leak. It just
Right. This is not a memory leak. It doesn't actually cause a memory leak by causing. If we call this function 1,000,000 times, this one wouldn't use any less or any more memory than doing this one. But time-wise, this one is slower, just because it's copying more bytes.
I got you.
So as far as how you want to access the members of your structure from a pointer, that's the preferred way. I'm just showing you this because, you know, we have been accessing pointers via this asterisk nomenclature, and you still could. So why don't we create another dog, another something, and then just ask the user for those values. Animal cat. Why don't I make it uppercase since I made dog uppercase? Whatever. And let's ask the user, please enter the name and then let's get that. Scanf %s. And now if we were just going to print the cat's name, it would be cat.name. I'm tempted to think that we need to use ampersand, but you don't use ampersand with strings. So that should be enough. And then let's print out our cat. I'm in too much of a hurry to finish this, so I'm just going to call print a cat. All right, cat's name is Floofy. All right, so the animal's name is Floofy and the breed is Blah. Let's see if we can initialize these values in the structure. I kind of forget, but I bet you can. I don't see any reason why you can't. I'm going to scroll up to the structure and do char name equals a 0, or just empty string would do the trick. Char breed is equal to empty string, and then age is equal to 0. I'm just doing that so, oh, and I closed GCC. Oh well. Alrighty then. It didn't like that. Okay. Forget that. That would have worked in C and in Java and a great many other languages, but C is old school, so we can't just depend upon everything working. What if I'd used initializers and tried to set it to 0 was my first instinct? Nope. Okay, never mind. It's irritating me enough that I want to Google it. Initialize C structure members. Well, that's not what I mean. Why can't we initialize members inside a structure? Why can't we do this? Because it's a definition and not a declaration. With recent C++, we can. Recent as in the past decade. All right. Oh, for Pete's sake. Okay, no. We're just going to say that we can't do it. What that page was showing us, if you cared to go look at it, is that after 1999, the C standard had a specification to where you can write an initializer for your structure. And then you could set the values that way. And we're not going to do that. We're just going to accept the fact that if you want to initialize the values, you better do it by hand, not inside your function.
How do we know what C standard GCC uses? Like, is there a command that shows that?
Yeah, good question. What C standard is GCC?
It says by default.
So you can specify that you want to enable and disable various versions of it. And I don't know which one is running by default. So while you're compiling it, you can specify which version you want it to go against. So for example, if I wanted to compile it to CIT2011, then I would do GCC minus std equals C11 J23.c. I'm sure that if we read all the man pages and whatever, we'd figure out which one it's running by default.
It says it uses their own.
Uses their own. Okay. So we've used a function that accepted these things. Let's create an array. Of animals. Animal, I'm just going to call this, I don't know. It's a flock. How many are going to be in our flock? 3. So let's make an animal and stick it into our array. Well, we've already got 2 animals. So flock subscript 0 is equal to our dog. Flock subscript 1 is equal to our cat. And let's make one more animal. Animal, flock, excuse me, animal, dog, cat, and bird. Name of the bird is Tweety. Tweety is a canary. And Tweety's 3. And so flock subscript 2 is equal to the bird. So we can iterate through our flock, calling one of the functions, for example, or whatever. So int I is equal to 0, for I is equal to 0, I is less than 3, I plus plus. Let's print A, that animal, flock subscript I. Going to add an extra print statement. Oh, and I already had I defined previously. And Dap, you're probably going to tell me that. Sorry about that. What have I done wrong?
You need to keep the first I, because now you're using it before it's declared.
Well, where am I defining it?
At the bottom somewhere there.
Oh! Okay. Yeah. Okay, so I'm going to leave that one, but then since I was using I down here, get rid of that one. Thank you. And then running it, /A. There we go. Please enter the animal name. I don't know, Fred. And so printed out Fred. Here's our flock. Lassie, and then Fred the cat, which is all messed up because I forgot to have us write the rest of that information in. And then the third animal is named Tweety. Okay, so let's go ahead and ask for not just the name. So please enter the name, comma, breed, and age separated by spaces. And so we're going to scanf the name, we're going to scanf %s for the cat breed, and then %d for the cat's age. So %s, %s, %d, cat.name, cat.breed, cat.age.
Well, you can do it like that.
Ought to be able to. Let's see if that'll work. Felix, cat, 23. Okay, that didn't work. I'm going to go back. Get rid of that. Please enter the name. Get the cat's name. And then I'm going to... Pardon me?
You probably should have put like %space s, because it'll probably take your like, well no, I don't know.
Yeah, I'm not sure about it, so I'm just going to do 3 of them in a row. Please enter the name, and then the breed, and then the age. And so the second scanf is for cat.breed, and the third, I needed to use an ampersand and I didn't. That was one mistake I made. But anyways, %d and then ampersand parentheses cat.name. I'm not sure if I need the parentheses. I'm going to leave them off. This first one, cat.age. Felix, cat, 29. Okay. Really wish that had worked.
Do you not have to use the ampersand for characters either? Or
Not for strings. For a single character, if you were going to use a %c to read that character in, then yes. If you had a character variable, you'd pass it in with an ampersand.
Oh. That's weird. I feel like I've done and before for a string.
We've seen that, yeah. Using ampersand and strings actually does not work, which actually it does work, which blows my mind. In my opinion, this should not work. I don't know why it does. I don't know what trick the compiler is doing to get that to work. Works great. So if you feel like doing it, I won't stop you. But in my mind, it shouldn't. I'm going to take them back out. It makes it consistent, though, right? I mean, okay. So you can use malloc to create your structures. Let's figure out the size of an animal. So size underscore t. I wonder what that remaps as. Is that just an unsigned int? An unsigned long? I don't know. Size underscore t bytes is equal to a size of the animal. We're doing that so that we know how many bytes we need to mallocate. Mallocate? Yeah, malloc.
Did it print?
Did it print when I ran it? Yes. Yeah. So if it's not for you, then I need to come help. Okay. So that compiled it, that ran it. Bob, cat, who's 100. Okay. So that seemed to work for me. Let me come help.
What is size underscore t bytes?
Google up size underscore t while I'm coming to look at that screen. Okay, so size underscore t is pretty much the same thing as unsigned int. The reason we're using it is so that we can malloc a new animal. Animal star PA1, a pointer to animal 1, is equal to malloc bytes. And then I would need to fill it in. PA1 hyphen greater than name. So you go to Harold. PA1 hyphen arrow breed equal to equine. And then PA1 hyphen arrow age is equal to 29. Like that. And let's print that out.
What's the point of making that bytes variable? Can you not just...
I could just do a size of right here.
Yeah.
Exactly. In fact, that's probably clear. So if I'm going to print out Harold the equine, I could do it like that, or else I could print it out by its address. Didn't we have one called with print AP, where it would take a pointer like that? Either one of those will work.
But they both are taking pointers.
Yeah, AP is the one that takes a pointer to the structure, so I could just pass the pointer straight in.
But why are you passing in a pointer on the print A?
I'm not passing in the pointer. Well, to turn the pointer into an object that could be printed, I had to dereference it, so that by the time it got here, it actually would be an animal and not a pointer to an animal. Just like if you have a pointer to an int I is equal to 3, and then you have int star p I. If you want to, and you set that equal to the ampersand of I, you could change its value. You could pass it to a function that accepted an int, void foo int I, whatever it was supposed to do. If you wanted to print that out, I really doubt that would compile, then you could call it like this, void I. That would certainly work, but you could also do this, foo star pii.
I understand.
Okay. Okay.
Because it's passed by value.
Right. Okay. I talked a big game. Let's see if that actually works.
You gotta make that size of lowercase.
Thank you. Yeah, size of needs to be all lowercase. Assignment to expression with array type. I should be using string copy to copy in there. I know better than that. All right. So instead of just saying that name is equal to that, this is an array. This is a string. I can't just copy into it like that. So instead I'm going to have to do this. String copy, PA hyphen name, comma, quote Harold. And I'm going to have to do the same thing for the breed. String copy, PA breed, comma, equine, like that. So Felix the cat, who's 100, and then we printed out everything, including Harold the equine, who is 29. Whenever you're done with something that you've mallocked, you should free it, and if you want to avoid memory leaks. Now in a simple little toy program like this, it wouldn't matter so much, but free PA1 and then set PA1 equal to null. So if we ever tried to use it again, we'd get an immediate error and we would know.
I'm confused about the memory leak thing. So when you do when you run the program, it only takes up that memory for the malloc, right? So how could it take up more after that?
Well, there's two types of memory that a program can allocate. When the program is... That's a bad way to approach it. Let's just say that when the program is compiled, it creates memory, space, bytes for everything we declare like this. But sometimes your program needs more. And when your program needs more and you call malloc, it asks the operating system to give it additional memory. And then the operating system gives the program that additional memory that it requests with the malloc.
I understand, but does that not only happen when you run the program?
Well, you run the program and it mallocs, but then what if it mallocked again and again and again and again? Each time it's grabbing a little bit more memory while it's running.
Yeah, but let's say you run it and then you close it, then you wouldn't have a problem.
Correct. Once the application is terminated, all the memory is freed.
So if we have like a function and we just kept calling the function, then it would just take up more and more and more.
Right. That's when your memory leak actually happens, is when the application continues to run without closing, and it's allocating but never freeing. So does that make sense?
Yeah. So let's say we wanted to like keep using it. Could you just free it and then reuse it again as long as you don't set it to null?
Oh, if you freed it and then reused it, that'd be bad news.
That'd be bad.
You'd have to malloc it again. But you could just keep reusing it rather than free it and reallocate it. Once you have memory, if you allocated a string of 180 characters long, you could just keep reusing that over and over and over. You don't have to free that string and then turn around and allocate a new one.
Oh, so the problem's when you keep allocating it.
Right. If you have repeated calls to malloc without associated calls to free, that's when you get your memory leaks. So when we had our array, we declared our array like that and we created several variables and set the array equal to that. That's usually not how you do it. Usually what you wind up with is you start mallocing and you create your array elements that way. And I don't want to botch this explanation, so malloc array of structures C. I wanted something easier than that, thank you. Well, let's just give it a shot. We're running to the point where I'm not going to be able to talk about linked lists for too long. But let's make another array of animals. Or we've already got one called flock. Let's malloc 3 animal star herd, it's a herd of animals, is equal to malloc, and I want 3 times the size of an animal, because I want 3 animals in this herd. And I seem to be missing an extra parentheses. All right, then I could do this, herd subscript 0 dot age is equal to 13, herd subscript 1 dot age is equal to 24, herd subscript 2 dot age is equal to 36. And we've seen that doing those names is a little bit, we have to use those string copies to copy into those, so I'm going to skip that for right now. So herd subscript 0, let's string copy into it, string herd subscript 0, and I'm going to get, this is John, and I'm going to copy and paste that. The second animal in the herd is named Fred, and a third animal in the herd is named Sue. And now for the breeds, so string copy.
Didn't you have to say?
You're right, I goofed that one. Thank you for catching me. Herd, I was just starting to wonder what I'd done wrong. Herd subscript 0 dot breed name, and then dot name, and dot name, And I'm going to copy that and change the reference's name to breed and give them different breeds. So herd 0 breed.
So you don't have to put the arrow when you do the
Herd, yeah, why am I not using the arrows? I would use the arrow if I had a pointer, if I was treating this like a pointer reference. But I'm treating it with array syntax, and with array you just use the name of the variable followed by its subscript, and then that is treated as a variable of that type. And since it is a variable of that type, we don't reference it via the arrow, we do a dot. Just like up here, when we had a variable of that type, we referenced its name like that. Now when we had a pointer to that type, we did it with the arrow. But this is herd subscript 0 is an animal. It's not a pointer. Let me see if this even runs before we start digging into that too much. Let's
so the herd itself is a pointer, but the element in the herd is like a variable.
exactly.
Yeah.
Right. All right, so dolphin, shark, and ostrich. John, Fred, Sue, 13. Now let's write a for loop that'll print them all. I equals 0 for I don't need that I is equal to 0 when I'm doing it on the next line. I is less than 3, I plus plus. Print a herd subscript I. Alrighty, and we found out that John's the dolphin and Fred's the shark and that Sue's the ostrich. If we were treating this array like a pointer, and we've seen that you can kind of flip between the two, you could do so. Now here's what it would look like. These three lines do the same as these three lines. It's just doing it with pointer nomenclature rather than an array nomenclature. If you started mixing the two, I'm not sure how you would. Like if it was an array of pointers, then yeah. We could have an array of pointers. Rather than 3 animals, we could have an array of 3 animal pointers. And my brain kind of freezes at how to demonstrate that. I would have to think about it beforehand.
Can you not just make an animal, then make a pointer to that animal, and then make an array of all the pointers?
Right, but how would I allocate that? I'm thinking I would have to do this. I think that would create an array of 3 animal pointers. Or, if we didn't use malloc on that spot, you know, animal star herd subscript 3, that's an array of 3 animal pointers, not 3 animals. And then when we reference them, I bet we would reference them with the dashes, with the hyphens. But I want to kind of leave that alone unless there are any other questions along that line. I think I'm inserting questions where there don't need to be any. What is a linked list? A linked list is a series of objects where the first one points to the next. Like this. where this object has a next member. And the next member can be set to null, or it can be set to the address of another object. So here's a structure called node. And each node has a piece of data, which could be a simple int, or as many pieces of members as needed to be. But then along with all those other members necessary to hold the data, there'd be one more called node, which is a pointer to another object. So if we had such an object, let's do it. We're running out of time, but let's do it. I want to create a node data type. So struct node, its data is an int, or you can use a float or whatever you wanted to, and then node asterisk next. So let's create a couple of nodes and then set their next pointers to each other. Let's do a type def for it. Type def node, or type def struct node, node with a capital N. So here, node N1, comma, N2, comma, N3. N1's dot data is equal to 1, 2, 3. N2's dot data is equal to 4, 5, 6, 3, 4, 5. N3's data is equal to 7, 8, 9, 6, 7, 8, something like that. Now N1's dot next equals the address of N2. And N2's dot next equals the address of N3. And N3's dot next equals null. That lets us know that that's the end of the chain. So node 1 will point to node 2. Node 2 will point to node 3. Node 3 will point to null. Fairly close to this slide version of it. Right there, except they called them A, B, and C. Like that. Now to have a linked list, you need to keep track of the head. The head is the first node in the list. So we're going to declare a pointer, node star head, and we're going to set head equal to the address of N1. That's the first element in the list. Now let's step through the list, printing out all of the nodes. So I'm going to create a pointer. I'm just going to call it PN, or CUR for current. P current, I'm not sure. Node P, how about current? We're going to start current by pointing it off to the head. And then while current is not equal to null, we're going to print out printf nodes data equals %d \n in quote, comma, current arrow data, because current is a pointer. And then we're going to set current equal to current dot next. We're going to get the pointer to the next object and assign it to our current. And it'll do that. Let's just see how this goes. Let's make sure this works before I give any more explanation about it. Someday I'll learn not to close SIGWIN every time. Here we go. GCC J23.c. Oh, needed that. Look at that. Here I was being all big and stuff and saying they were appropriate. I mean, the same thing. Down here I botched something, and I'm going to delete those rather than take the time to figure it out, or at least I'm going to comment them out. This herd age, and herd age did not work.
Does C not have a multi-line comment?
It does actually. A multi-line comment is open that, like that, and then the end of it is //. That's a multi-line comment.
Just like Java. Or Java is just like C.
Yeah, yeah. Java stole it from C. As a matter of fact, // wasn't in the original C spec, and all you had were multi-line comments. All right, let's see if there's another problem. Current is undeclared. A node type name node. Oh, I forgot my semicolon. Excuse me. Whenever you define a structure, the last thing in it has to be a semicolon. Assignment from incompatible pointer type. n1.next equals ampersand n2. Current is a pointer. Did you mean to? Okay, that is true. I understand that one being an error.
You have to make that node capital.
In this case,
Yeah.
I don't know how that would work because it hadn't hit the type def yet. But this definitely has to be a that. Okay. None of the changes I made are going to fix it. Request for member next in something not a structure or a union. Well, I had my other examples cooked up, and I thought that this was an easier one, and I should not have flown by the seat of my pants when I did this. Because it's going to be an unsatisfying end to the lecture. n1.next is equal to ampersand n2. Assignment from incompatible pointer type. Why is it saying that that's an incompatible pointer type? .next is a node pointer. It worked all the way here. Did it not? If I had just stopped there and the rest of this was commented out, would it have compiled? No. Alrighty. Got to revise it a little bit. I apologize for that. I'm going to go ahead and start using my type def again. Type def struct node with a capital N. All right. So down here, node star first is equal to malloc size of node. And so first value, first data is equal to 1, 2, 3. Now let's get another one. Node star second is equal to malloc size of node. And second data is equal to 4, 5, 6. And then the first pointer, first hyphen next is equal to second. The first item is now pointing to second. Now let's create one more, the third one. Node star third is equal to malloc, size of node, thirds dash greater than, hyphen greater than, data is equal to 789. And the second one points to this. So second hyphen greater than next is equal to third. And thirds next, since we don't have any more, third hyphen greater than next is equal to null. Before we even go any further, let's make sure that that compiles cleanly. Oh, yeah. All right. And when you call malloc, you have to cast its type. So see each one of these calls to malloc, it needs to be cast as a node pointer. So put asterisk node asterisk, parentheses node asterisk in front of each node, each call to malloc. And I guess it's actually malloc and not mallow. Assignment from incompatible pointer type. Oh. Struct node star. That probably would have fixed them all. Yeah. My first example would have worked as well if I just remembered to add the word struct there. Since I didn't have the type def in existence yet, I couldn't just do node star with a capital N. But since I can't do that, I have to use the word struct whenever I'm specifying a pointer to it in lowercase n. Okay, so anyways, now we have three nodes. The first one, the second one, and the third one. So I'm going to create a pointer to a current node. Node star current is equal to the first. Node star cur is equal to first. And then while cur hyphen greater than next is not equal to null, let's get that data out. Printf %d or node data equals %d backslash n end quote comma cur hyphen greater than data, and then cur is equal to cur hyphen greater next. Skip to the next one. And keep doing that until we find a pointer that is set to null in it. Please work. All right, I thought we had several of them. I thought that we didn't just have 1, 2, 3, 4, 5, 6, and 7, 8, 9. So, to my thinking, it shouldn't have stopped there. We should have printed out 1, 2, 3. We should have printed out 4, 5, 6. We created a third pointer. We gave it some data, and we set the second one's next, pointing to that one. Printf %p, %p, comma, %p, comma, %p, backslash n, and I'm going to print out first, second, third, comma, and then first hyphen next, comma, second hyphen next, comma, third hyphen next. So if we look at our pointers, here's the address of the first one, here's the address of the second one, and here's the address of the third one. And the first one's next pointer points to that one. Excuse me, the first item's next reference points to the second item. The second item's next reference points to the third item. The third item's next reference points to null.
Is your while loop, see how it starts with cur next? you just need to do cur?
I need to do cur. You are exactly right. Exactly. So while the current is not equal to null, while we are not sitting on a null pointer. All right, my faith in the universe is now restored. Thank you for that. All right, and so we printed out each node. Node 1, 2, 3, 4, 5, 6, and 7, 8, 9. So I'm going to have to do a better lecture about linked lists than that. And I do have a PowerPoint here, but unfortunately the linked list that they give us is written in C++, which is not of use to us. So I'm going to modify the PowerPoint. Here is a linked list over PowerPoints. Excuse me, yeah, the PowerPoint linked list. So linked list is an abstract data type. The various things you care about doing with a linked list are inserting into the middle of it, finding something in it, deleting, printing the linked list, and I would say append to the end. They don't show appending to the end. So a linked list, this one's one that's not showing the little pictures, is a series of elements where the next points to the pointer of the third. And so if we had our linked list that looked like this, and we wanted to delete element B, what you got to do is you set A's dot next equal to B's dot next, right? So now A is not pointing to him, it's pointing to that. And then you have to free that one, or else you'll have your memory leak. And so when you start at the beginning of a linked list, start ahead, and you keep going until your pointer is null. When you append to it, you just go all the way until you find a dot next that is equal to null, and you create a new item, and you set that dot next equal to the address of the new item. So append, you search the entire list for the item, or for the item where the next is referencing null, and you create a new one, and you set that next reference to that current item. To delete one, you find the one that matches, and then you set the node's next of the prior one equal to the one after it, and then you free that one. So that is about enough of that.
Can I see the code?
Sure.